Let's compute the region S from a region R. In this particular problem, we have the region R, which is represented by this triangle, and we have a transformation T, where x is equal to 3u plus 2v, and y is equal to 3v. So what we want to do is to see what the actual image is of R using this transformation. So in order to do that, you notice that this is really going in the wrong direction. We need the transformation that moves R into S. So first what we need to do is worry about an inverse transformation. And that's not difficult to do. You can always just solve this using matrix methods, but this one's very simple. We can actually do it by observation. Notice here we can easily solve for b by dividing y by 3, and we're done with that particular variable. And now we want to isolate the u. So if you look at this, we could multiply the y by 2 and the x by -3 to get rid of the b's. So more specifically, we'll say 2y minus 3x is 2 times 3v minus 3 times the quantity 3u plus 2v. So notice we get a 6v here and a negative 6v here. They go away, they absorb, and we're left with negative 9u. Okay, so that defines the inverse transformation as long as we divide by -9. So in this case, we divide the 2y by -9, and we divide the -3x by -9 and get this. And notice I left these unreduced, this one in particular, just to make the arithmetic easier as you do the computations. And then of course the v we just fill in right here is y over 3. So we have our inverse transformation. Now, most students think, okay, I just need to figure out what happens to the vertices and I'm done. And that would probably be more than sufficient. But I do want to say a little more about this as we look through these computations. So now we want to see what happens to 0, 0. So you replace x with 0, y with 0 here, and you get 0, 0. Now again, just using this formula, we want to see what happens to 2, 3. So you replace x with 2, y with 3. These are very simple computations. You get the point 0, 1. And if you replace x with 3 and y with 0, this point here, you get the point 1, 0. So you're thinking, okay, I've got 0, 0, 0, 1, 1, 0. That must be what I have because S has to be a triangle. Well, this is a linear transformation, and the linear transformations preserve these vectors in a very nice way. But maybe you don't know that, or maybe you're not really sure, and you want to check into this. So, for instance, any linear transformation can be written as a matrix. And so what we can do is think of matrix multiplication. Just go ahead and fill in these numbers. 3 over 9, -2/9, and then 0, and then 1/3. So this would be a matrix representation of T inverse. And what I want to do is write all of these sides of this triangle as vectors. So the vector from A to C we can write as the vector 2, 3. The vector from A to B we can write as the vector 3, 0. And then of course the vector from B to C, just doing C minus B, we can write as the vector -1, 3. Just computations we did at the beginning of our Calculus 3 course. And then what I just want to do here is just to apply the matrix, the inverse T, to all of these vectors. And again, this is just matrix multiplication. So when you do this, you get a -3/9 minus a -6/9, which is a -9 over 9, which is -1. And then here you get a 0 plus a 3 over 3, which is 1. So that's how you do the computations with the matrix multiplication. Very simple, college algebra, right? And so what we see is that BC gets transformed into that vector. AC is transformed into the vector 0, 1 right there. And AB is transformed into the vector 1, 0. But these computations up here help us to know how this is positioned. That is, we know that, for instance, when we look for B, 3, 0 is transformed into 1, 0. So the initial point of this vector is right there. And then the point 2, 3, as we noted, is transformed into 0.01. So the terminal point is right there. So this vector starts here and ends here. So we see that everything works out nicely. All of the sides of the triangle move into sides of this triangle, and we see that the region S in comparison to the region R is a lot easier. For instance, if we needed to do a computation with this region, it would be much easier because it's so simple. The region R is much more complicated. So this is really the essence of the change of variables theorem. We want to be able to transform a region into a simpler one so that we can actually do the computation with ease. Okay, and we are done.